Welcome, my dear learners, for this course on Design of Machine Elements 2. In this final module, we were discussing on design of clutches, brakes and bearings. So far, we have completed our discussion on clutches and brakes. From today's lecture, we are heading to discuss lubrication and bearing. Before heading to design bearings, first let us discuss the important topics and terminologies which we employed in design of bearings. Coming for the first one, that is lubrication. Lubrication is a process of reducing the friction between the two contacting surfaces by using a medium called lubricant. Now, what is the meaning of lubricant? Lubricant are one which reduces the friction between the two contacting surfaces or between the two rubbing surfaces. When two surfaces which are in contact are subjected for rubbing, if I employ lubricant, then we can provide lubrication. So lubrication is a process of reducing the friction between the two rubbing surfaces. Coming for classification of lubricants. Lubricants are broadly classified as liquid lubricant, semi-solid lubricant and solid lubricant. Coming for liquid lubricant, the best example is oil. That is, SAE oils which we use in automobiles are best examples for liquid lubricant. Coming for semi-solid lubricant, the very good example is grease. Grease is a very good example for semi-solid lubricant. Coming for solid lubricant, the examples for solid lubricant are graphite and wax. Wax and graphite are very good examples for solid lubricant. Next, moving for the important properties of lubricants. The first important property is viscosity. As you all know, viscosity is the resistance for flow, or it is the resistance for shear from one layer of a fluid to the another layer. For lubrication purpose, when we employ it in bearings, the lubricant should not shear off, or it should not shear the thin film of lubrication that it has formed. So therefore, the lubricant what we employ in bearings, which is required to form a very thin lubricating film, should have very high viscosity. If it has very high viscosity, then it can operate for very high pressure and high loads. So therefore, high viscosity lubricants are desired in case of bearings. Next, moving ahead for second property, that is oiliness. Oiliness is nothing but the ability to produce wettability and surface tension on the surfaces which are in rubbing with each other, and oiliness is also defined as the ability of an lubricant to withstand the thin film layer of lubrication which it has formed between the rubbing surfaces. It is an ability of a lubricant to maintain the thin film of lubrication. Next, moving ahead for next is flash point. Coming for flash point, it is the temperature at which the oil produces enough vapors that can catch fire momentarily. For good lubricant, this flash point should be higher than that of the operating temperature. Next, fourth one is fire point. Fire point is defined as the temperature at which the oil vaporizes such a way that it is enough to catch fire. For good lubricant, the fire point should be higher than that of the operating temperature. Next is power point. Power point is the temperature at which oil ceases its flow. The temperature at which lubricant ceases its flow when it is cooled. For good lubricant, the power point should be less as much as possible because it should not cease its flow. It is cooled. Next point is cloud point. Cloud point is nothing but the temperature at which oil appears to be cloudy in nature when it is cooled. So these are the important properties of lubricant and the desired conditions of these properties. Next, moving ahead, we have to discuss bearings. What are these bearings? Bearings are the machine members which supports, guide and restrain the moving elements. Bearings are one which take up load, guide and restrain the moving elements. If I consider a shaft, so shaft is a very long slender member which is always subjected for rotation, rotary motion. The part of a shaft which is in contact with the bearing is termed as journal. The part of the shaft which is in contact with the bearing is called as journal. Coming for classification of bearings, we have the broad classification of bearings as sliding bearings and roller bearings. Under sliding bearing, we have full journal bearing, partial journal bearing, full journal bearing, partial journal bearing, thrust bearing, and then we have sliding bearing, that is slide bearing, and hydrostatic bearing. Whereas under rolling bearing, we have two more categories, that is ball bearing and we have roller bearing. If I want to know the further classification of ball bearing, so ball bearing is further classified as simple ball bearing and deep groove ball bearing. That is simple ball bearing and deep groove ball bearing. Coming for classification under roller bearing is again classified as straight roller, bearing and tapered roller bearing. So this is the broad classification of bearings. And now the mechanism of developing the lubrication film by using the pressurized fluid are broadly classified as hydrostatic lubrication, hydrodynamic lubrication and elasto-hydrodynamic lubrication, which is a very important concept one should know in design of bearings. The next concept is mechanism of developing lubrication film using pressurized fluid, which is of three types. First one is hydrostatic lubrication. Second one is hydrodynamic lubrication, and third one is elasto-hydrodynamic lubrication. So these are the three different mechanisms of developing lubricating film between the rubbing surfaces. Coming for hydrostatic lubrication. In this method of lubrication, we provide the lubrication between the two rubbing surfaces, that is between the journal and bearing, by using a pressurized fluid impinging by the holes provided in the bearing. So this pressurized fluid that is impinging on the surface of the journal will cause a thin film of lubrication between the journal and bearing. So in case of hydrostatic bearing, we will use the supporting equipments in order to supply the pressurized fluid between the journal and the bearing through the holes provided in the bearing. Next, coming for hydrodynamic lubrication. In case of hydrodynamic lubrication, the thin film of lubrication is produced as the journal rotates. inside the bearing. At high speeds, the journal moves towards the center, and at very high speeds, the journal and bearing rotates concentrically. Then there will be a formation of thin film of lubrication between the journal and bearing. But in case of starting and stopping, the load will act eccentrically on the shafts, and the shaft will come in contact with the surface of the bearing. So the disadvantage of hydrodynamic lubrication is starting and stopping. Once the journal starts rotating, as it rotates, it starts moving towards the center, and there will be enough gap between the bearing surface and the journal. A thin film of lubrication is provided. Once, if you want to stop the journal, so then at low speeds the journal will move eccentrically, and as it slows down, it will come in contact with the surface of the bearing, and it causes the friction and heat generation will be formed. This is known as boundary lubrication. If a thin film of lubrication is provided, then it is called as stable lubrication. The hydrodynamic lubrication will causes boundary lubrication during starting and stopping of the journal. So hence, the combination of these two will help us to provide proper lubrication. During starting and stopping, we can use hydrostatic lubrication. By using pressurized fluid, we can create the gap between the journal and bearing, thereby we can provide the thin film of lubrication. While running, we can use hydrodynamic lubrication. The disadvantage of hydrostatic lubrication is that it requires additional equipments, whereas hydrodynamic lubrication does not require any additional equipments to supply the pressurized fluid. So both have their own advantage and disadvantages. Next, coming for elasto-hydrodynamic lubrication. As the name elasto states that when the bearings are subjected for loading conditions, the journal have some elasticity in it, so which causes the flattening of the journal. So this negligible flattening and the very high viscosity of the lubricant will cause a thin film of lubrication between the journal and the bearing. That is, as we all know, if I analyze a mild steel in an UTM, we observing the elastic limit and later we observe the yield point. So similarly, when the journal is subjected for loading condition, it will have some amount of elasticity, so which causes a negligible flattening of the journal. A very minimum gap will be existing between the journal and the bearing, and the high viscosity of the lubricant, these two in combination provide a thin film of lubrication between the journal and the bearing. So hence the name elasto-hydrodynamic lubrication. So these are the very important mechanisms of providing lubrication. For better understanding of hydrodynamic lubrication, refer page number 361 of our design data handbook, page number 361 and figure 15.18 in design data handbook, which is written by K. Mahadevan and K. Balaveera Reddy. We are referring 4th edition. So refer page number 361, figure 15.18. He has clearly indicated how the lubrication film is formed between the journal and bearing. With this very brief introduction to the theoretical aspects of lubrication and bearing, let us derive Petroff's equation for lightly loaded bearings in today's lecture. Next, moving for derivation of Petroff's equation, let us consider a journal and bearing as shown in the figure. The part of shaft which is in contact with the bearing is termed as journal, and let us have a bearing like this. Let us take the bearing surface and the journal. So journal is rotating with an angular velocity omega, let the diameter of the journal be small d and the diametrical clearance will be, including the gap, let it be d plus diametrical clearance capital C, let it be d plus C, and the radial clearance, let us call it as h, which is equal to diametrical clearance by 2. Let us call this as h, which is equal to diametrical clearance by 2, and the gap between the journal and bearing is filled with lubricant. A thin film of oil lubrication is provided between the journal and bearing, which is uniform. Let us have the lubricant. This is journal and this is bearing, and we have oil filled between the journal and bearing. In order to analyze or derive expression for coefficient of friction using Petroff's equation, we have some important assumptions. The assumptions made in the derivation of Petroff's equation are: the first one is the bearing is lightly loaded. Hence, since the bearing is lightly loaded and the journal rotates at very high speed, since the journal is rotating at very high speed, so therefore the bearing rotates concentrically. Next, the gap C, that is H plus H, that is equal to C. The gap C is completely filled with oil. The gap C between the journal and bearing is completely filled with oil. Next, the oil used has very high viscosity. The oil used has high viscosity. So since the oil used has very high viscosity, it can resist shear. And next is that end leakages are neglected. End leakage of oil is negligible. There is no end leakage. So these are the 6 very important assumptions made in the derivation of Petroff's equation. Petroff's equation is employed only for lightly loaded bearings. And let us define the terms as small d is diameter of journal, capital D is diameter of bearing, next we have L is the length of bearing, let capital C be diametrical clearance, and H is the half of diametrical clearance, and we define one more term xi called diametrical clearance ratio. Diametrical clearance ratio, hence xi is equal to diametrical clearance by diameter of the journal, and let small n be the speed of the journal in RPS. Speed of the journal in RPS, revolutions per second. Capital N stands for revolutions per minute. Let us define the terms like this and let us have the notation for load as W. W is load applied and mu is coefficient of friction. And let us define Z as absolute or dynamic viscosity. Absolute or dynamic viscosity, and P as the bearing pressure. Now, from Newton's law of viscosity, we know that from Newton's law of viscosity, shear stress tau is proportional to rate of shear strain. Here the rate of shear strain is U by H. That is, shear stress is equal to absolute or dynamic viscosity times the rate of shear strain, that is U by H. Now let us define U as velocity, which is equal to pi d n meters per second. So substitute for U, we get shear stress is equal to absolute viscosity times U is pi d n divided by H is nothing but diametrical clearance by 2. So therefore shear stress will become 2 times absolute viscosity into pi into diameter into n divided by c. So this is the value of shear stress. In order to avoid confusion, let me write 2 like this, because 2 and z might get confused. Now we know that stress is equal to force by area, hence the shearing force is equal to stress times the area. Now we know that the area which is in contact with the lubricant is surface area, so therefore frictional force will become 2 times dynamic viscosity pi d n by diametrical clearance C times the surface area pi d n. The journal and the oil are in contact with the surface area of the journal. Hence, if I simplify, I will get F is equal to 2 times pi square d square Zn into L by C. So hence the torque will become torque P is equal to force into perpendicular distance. The perpendicular distance is diameter by 2, that is d by 2. Hence the torque will be 2 times pi square d square Z n L divided by diametrical clearance C times d by 2. Let us cancel off 2 and 2. Now I can write C by D as xi. So T is equal to pi square d square Z times NL by xi. Xi is the diametrical clearance, that is xi is equal to C by D. I have taken this D to the denominator's denominator, because diametrical clearance ratio is diametrical clearance by diameter of the journal. So let us take this as equation number 1. Now we also know that the torque due to friction is given by friction force into perpendicular distance. So therefore torque due to friction is frictional force. If W is the load applied, then frictional force is coefficient of friction mu times the load applied, is the frictional force into distance is diameter by 2. This you people already know, because frictional force by load applied is equal to coefficient of friction. Hence frictional force is mu times the W into perpendicular distance is the torque. Frictional force into perpendicular distance. Now we know that the pressure acting on the bearing is nothing but load divided by projected area. So if I project this and analyze the area, it will look like a rectangle. If I see the journal in the side view, it will look like a rectangle with height L, and width will be diameter. So therefore the projected area will be length times the diameter. Load by projected area is pressure. So therefore I will get the equation for load as pressure times the projected area. So now if I substitute, I will get torque as mu times pressure times the projected area is the load into d by 2. So therefore torque T is equal to mu times P L d square by 2. Let us take it as equation number 2. So now equate equation 1 and 2, you will get equating equation 1 and equation 2, we will get mu PL d square by 2 is equal to pi square d square Zn L by Z. So if I simplify, I can cancel off d square, L and L. Hence I left out with coefficient of friction mu is equal to 2 times pi square into, I can have a term as Zn by P times 1 by Z. So this is the expression for Petroff's equation. This is called as Petroff's equation. This is available in our data handbook at page number, refer page number 353, equation 15.4a of design data handbook. So the Petroff's equation what we have derived is available in page number 353, equation number 15.4a of our design data handbook written by K. Mahadevan and K. Balavir Reddy. We are referring 4th edition. So this completes the expression for Petroff's equation for lightly loaded bearings. With this very brief introduction to design of bearings,